Look around the room you are in. Feel the depth of it, the space between you and the far wall, the way objects sit at different distances, near and far, the three-dimensional fullness of the world. Reach out your hand and move it through the empty air, through the depth in front of you, and feel how real that depth is, how solid and obvious and undeniable. The world has three dimensions: length, width, and depth. You move through all three. You have never had the slightest reason to doubt it. The three-dimensionality of reality is perhaps the most basic, most certain fact of your entire existence. And yet, some of the most serious and respected physicists alive have been led, by the mathematics of their own theories, to a possibility so strange it is hard to even put into words. The possibility that the depth you are looking at right now, the third dimension, the very fullness of space itself, might not be fundamental. That all the information describing this entire three-dimensional room, you, the objects in it, the space between them, every detail of the depth you perceive, might actually be encoded on a distant two-dimensional surface, and that the rich, deep, three-dimensional world you experience might be something that emerges from that flat surface, the way a three-dimensional image emerges from a flat piece of holographic film. The idea has a name. It is called the holographic principle, and it is not science fiction, and it is not the idle speculation of cranks. It emerged from the hard mathematics of black holes. It is taken seriously by some of the finest minds in physics, and it suggests something that genuinely strains the mind to its limit. That reality, at its very deepest level, may be organized in a way utterly unlike the three-dimensional world it presents to us. Now, before we go any further, let me be absolutely clear about one thing, because it matters, and because this idea is so easily misunderstood. The holographic principle does not say that the world is fake. It does not say that you are not real, or that the room around you is an illusion, or that nothing exists. The world is real. You are real. The depth you perceive is real depth. The chair is a real chair. What the theory suggests is something more subtle, and in a way more profound than mere illusion. It suggests that the deepest layer of reality, the most fundamental description of what is actually going on, may be lower dimensional than the world we experience. That the three-dimensional space we live in may be, in a precise physical and mathematical sense, encoded on or emerging from a lower dimensional surface. The world is not a fake, but the world may be, at its foundation, something far stranger than the simple three-dimensional space it appears to be. And that distinction between fake and deeply different is the whole heart of this story. Tonight we are going to journey into one of the strangest and most profound ideas in all of modern physics, an idea that suggests the very dimensionality of reality may not be what it seems. We are going to start with something familiar, the ordinary hologram, and understand the genuinely surprising trick. At the heart of it, the way a flat surface can hold a three-dimensional image. We are going to follow physicists into the study of black holes, where they discovered a shocking and unexpected fact about information, a fact that pointed, like a signpost, toward holography. We are going to confront the bold principle they were led to, the claim that everything in a region of space can be described by information on its boundary. We are going to look at the deep mathematical discovery that turned this from a wild idea into a serious theory. a discovery that showed, in precise detail, how a universe with depth and gravity could be exactly equivalent to a flat surface without them. And we are going to sit with what it might mean. The vertiginous possibility that depth itself, and even gravity, may be emergent, woven out of something deeper and flatter. That the solid three-dimensional world is the surface appearance of a reality, organized in a way we are only beginning to grasp. But to understand how a three-dimensional world could be encoded on a two-dimensional surface, we have to start with the one place where we already know this trick is possible, the one everyday object that already does exactly this, that already takes a flat surface and stores within it the full three-dimensional structure of a scene. We have to start with the hologram itself. But first, let the strangeness of the claim sit with you for just a moment longer, because it is the kind of idea that the mind wants to slide past without really absorbing, and it deserves to be absorbed. You are looking, right now, at a three-dimensional world. Not a picture of one, not a representation, but the genuine article, with real depth that you can move through, real distances you can cross, real space all around you. And the suggestion on the table is that this depth, this third dimension that seems so obviously basic, so clearly part of the bedrock of what is real, might be the equivalent of the floating image above a piece of holographic film. Something that genuinely appears and that you genuinely experience, but that is encoded at the most fundamental level, on a surface with one fewer dimension, a surface you can never reach or see, perhaps unimaginably far away, perhaps at the very boundary of the universe itself. The depth in front of your eyes in this view would be the projection, and the truth of it would lie flat elsewhere on a surface. It is the kind of thing that sounds like the rambling of a dreamer, and yet falls out of the hardest mathematics we have. I want you to hold that tension throughout everything that follows. The tension between how absurd this sounds and how seriously it is taken. Because that tension is exactly what makes the idea worth your attention. If a stranger said this to you on the street, you would walk away. But it is not a stranger on the street saying it. It is the mathematics of black holes, the equations of quantum gravity, the careful work of physicists at the world's leading institutions, all pointing with surprising consistency toward the possibility that the depth of the world is not what it seems. When an idea this strange arrives from a source this rigorous, the right response is not to dismiss it and not to panic, but to lean in carefully and try to understand how on earth anyone could be led to such a conclusion. And to do that, we have to begin where the word hologram itself begins, with the real, physical, everyday objects that already perform the impossible-sounding trick of holding three dimensions on a flat surface. You have seen holograms. They are on credit cards and banknotes and product packaging. Those shimmering images that seem to have depth, that shift and change as you tilt them, that look three-dimensional even though they are printed on a flat surface. And most people, glancing at them, assume they are just a clever visual trick, a kind of fancy sticker. But a true hologram is something far more remarkable than that, and the way it works contains the seed of the entire idea we are exploring tonight, because a hologram genuinely stores three-dimensional information on a two-dimensional surface. It is not a flat picture pretending to have depth. It is a flat surface that has truly captured the full three-dimensional structure of the light from a scene in a way that lets that three-dimensional structure be reconstructed. This is genuinely strange when you first encounter it, and it is worth dwelling on, because most people have never been told what a hologram actually is. We are used to the idea that to capture a three-dimensional thing you need a three-dimensional record. That depth requires depth to store it. A sculpture captures a face in 3 dimensions. A photograph flattens it into 2 and loses the depth forever. So the natural assumption is that depth is a kind of information that can only be held in a volume, that you cannot put the fullness of 3 dimensions onto a flat sheet without throwing something away. The hologram quietly shatters that assumption. It demonstrates, with ordinary light and a piece of film, that the complete 3-dimensional information of a scene can, in fact, be held on a 2-dimensional surface perfectly, with nothing lost, ready to be unfolded back into full depth whenever the right light is shone through it. The depth was not stored as depth. It was stored as a flat code, and yet the depth comes back complete. The trick lies in what the surface records. An ordinary photograph is a record of how much light arrived at each point, a simple map of brightness and color. But it ignores something crucial about light. That light is a wave, and waves carry information not just in their brightness, but in their timing. In the precise way their crests and troughs line up, what physicists call the phase. When light reflects off a 3-dimensional object, the light from the near parts and the light from the far parts arrives slightly out of step. The waves shifted relative to one another according to the exact distances they traveled. That shifting, that phase information, is precisely where the depth is hidden. An ordinary photograph throws it away. A hologram captures it by letting the light from the object interfere with a clean reference beam, so that the alignment of the waves is frozen into a fine pattern of light and dark across the film. The depth of the scene is encoded in the geometry of that pattern, in the spacing and curving of its countless fine lines, a complete record of the 3-dimensional structure of the light, written flat. To understand how, consider the difference between an ordinary photograph and a hologram. An ordinary photograph records only the brightness and color of the light, landing on each point of the film. It captures a flat snapshot, a single point of view, and that is why a photograph looks flat. It has thrown away the 3-dimensional information. But a hologram records something more. It records not just the brightness of the light, but the full pattern of the light waves themselves, including the subtle information about the direction and distance the light traveled, encoded in the way the waves interfere with one another. When the light bouncing off a 3-dimensional object is captured along with a reference beam, the 2 sets of waves overlap and create an intricate interference pattern, a dense, fine pattern of light and dark, recorded across the flat surface. That pattern looks like meaningless noise to the eye, nothing like the object, but it contains, encoded within it, the complete 3-dimensional structure of the light from the scene. And here is the magic. When you shine the right light back through that flat interference pattern, the pattern bends and reconstructs the light waves exactly as they originally came from the object, recreating the full three-dimensional image, floating in space with real depth so that you can look around it slightly, see different angles, perceive its solidity, all reconstructed from a flat surface covered in a fine pattern. The three-dimensional scene was never stored as a three-dimensional thing. It was stored as a two-dimensional pattern, a flat code, from which the third dimension is reconstructed. The depth was encoded on the surface. This is the genuine and astonishing fact at the heart of holography, and it is worth letting it sink in because it establishes something that sounds impossible, but is, in this everyday case, simply true. The complete information about a three-dimensional scene can be stored on a two-dimensional surface, and the third dimension can be reconstructed from it. Now, an ordinary hologram is still, of course, just an image. The object itself is not really there, only a reconstruction of the light from it. So you might think this is just a neat trick of optics with no deeper meaning. But hold on to the core idea because it is about to become something far more serious. The core idea is this: three-dimensional information can live on a two-dimensional surface with no loss, the depth fully encoded in the flat. And the radical suggestion of the holographic principle is that this is not just a trick we can do with light and film, but something fundamental about the nature of reality itself, that the universe may store the information of three-dimensional space on two-dimensional surfaces as a basic feature of how it is built, and that we, living inside the apparent three dimensions, may be like the reconstructed image, real and full and deep, but encoded at the deepest level, on a flatter surface than we can perceive. There is a crucial difference, though, between an everyday hologram and what the holographic principle proposes, and noticing it actually makes the physics more interesting rather than less. An everyday hologram is a representation of something else. The object it depicts exists separately, somewhere, and the hologram merely encodes the light that bounced off it. So, an ordinary hologram really is, in a sense, just an image, a copy, less real than the thing it represents. But the holographic principle is not saying that our world is a copy or an image of some other, more real three-dimensional world located elsewhere. It is saying something stranger and, in a way, more respectful of our reality. That there is no separate three-dimensional original, that the flat boundary and the three-dimensional world are two complete descriptions of one single reality, equally valid, neither a mere copy of the other. We are not the image of some distant, real object. We are the three-dimensional face of a reality whose other, deeper face is flat. The everyday hologram is the closest familiar analogy we have, and it is a good one for grasping how depth can live on a surface, but it can mislead if it makes us think of ourselves as mere pictures of something realer elsewhere. We are not pictures. We are one genuine aspect of a reality with two faces, one deep and one flat. Keep that refinement in mind, because it protects against the easy despair the hologram image can provoke. When people first hear that the universe might be a hologram, they often imagine themselves as flickering projections, insubstantial, less than real, mere shadows cast by some truer thing. But that is the wrong picture. The right picture is of a single reality, fully and equally expressed in two ways, a three-dimensional way that we inhabit and experience, and a flat informational way that is more economical, and perhaps more fundamental, but not more real in the sense of making us less so. We have all the reality there is to have. We simply have it in a form that may also be expressible completely on a surface. And with that refinement held firmly in mind, we can take the analogy for what it is worth, a doorway into one of the strangest ideas in physics, without letting it frighten us into thinking ourselves unreal. That is an enormous leap to make, from a shimmering image on a credit card to the fundamental nature of the universe. And no physicist would have made such a leap without bait being forced to, without some powerful clue pointing in that direction. The clue did not come from holograms at all. It came from the most extreme and mysterious objects in the cosmos, the places where gravity becomes so strong that it crushes everything, including, as it turns out, our intuitions about where information can live. The clue came from black holes. To understand the clue, we need to talk about information and about a deep and surprising connection between information and the physical world. Information sounds like an abstract thing, the contents of a book, the data on a drive, something separate from physics. But physicists have come to understand that information is deeply physical, that it is tied to the real properties of matter and energy, and crucially, that there is a limit to how much information can be packed into any region of space. This connects to a concept called entropy, which is roughly a measure of how many possible microscopic arrangements a system could have, how much hidden information it contains. It is worth being a little more careful about what we mean by information here, because the word gets used loosely, and the precise meaning is what makes the black hole result so striking. Information in physics is not about meaning or messages. It is about distinguishable states, about the number of different ways the tiny constituents of a system can be arranged while still looking the same from the outside. A box of gas looks the same from the outside regardless of exactly where each individual molecule is. But the molecules could be arranged in an astronomical number of different specific configurations, and the count of those hidden configurations is a measure of the information the system contains. The more possible arrangements, the more information. And this hidden information is physical and real. It has measurable consequences. It obeys strict laws. It cannot simply be conjured or destroyed at will. It is as much a part of the physical inventory of the universe as energy or mass, a real quantity that the laws of nature track and conserve. So when physicists ask how much information a black hole can hold, they are asking something precise. How many distinct underlying configurations can correspond to a given black hole? How much hidden detail can be packed away behind its horizon? And the answer, that this number is set by the surface area of the horizon rather than the volume within, is a statement about the fundamental capacity of that region of space to hold distinguishable states. It says that the number of possible configurations is fixed by the boundary, not the interior, which is precisely the surprising thing, as though the surface, not the volume, were the true ledger of everything the region could contain. And for ordinary things, the amount of information you can store scales with volume. A bigger box holds more stuff, more information. Double the volume, and you can roughly double the information. This is intuitive. Information lives inside things, throughout their volume, So the more volume, the more information. That is how it works for everything in ordinary experience. It helps to make this concrete because the idea that information scales with volume is so intuitive that we rarely notice we are assuming it. Imagine you want to store data, any data, in some region of space. You might use atoms, each one set to a particular state, like tiny switches. Naturally, the more space you have, the more atoms you can fit, and the more atoms you can fit, the more switches, and the more switches, the more information. And atoms fill volume. So the bigger the volume, the more atoms, the more information. A library holds more books than a shelf because it has more room throughout its three-dimensional space. A larger hard drive holds more data because it has more material in which to encode it. Everywhere we look, in everything we build and everything we observe, the capacity to hold information grows with the volume available, with the three-dimensional room inside. This is so reliable, so universal in ordinary experience, that it seems less like an assumption and more like an obvious truth about the nature of space and information. And this is exactly why the black hole result was such a shock. It did not merely tweak this picture, it overturned it in the one place where gravity is pushed to its absolute extreme. Because if you try to pack more and more information into a region, using more and more matter, you are also packing in more and more mass and energy, and mass and energy bend space through gravity. Push hard enough, cram enough into a region, and the gravity becomes so intense that the whole region collapses into a black hole. So a black hole represents, in a sense, the maximum possible concentration of information in a region of space, the densest that information can ever be packed before gravity seals it away. And precisely there, at that ultimate limit, the information turns out to depend not on the volume but on the surface area, the very case that should hold the most information, the most tightly packed three-dimensional volume imaginable. Instead, has its information capacity set by its two-dimensional boundary. The limit of information storage is a surface, not a volume. That is the deep and disorienting lesson the black hole teaches. Then physicists turned their attention to black holes, and everything changed. A black hole is a region where gravity is so intense that nothing, not even light, can escape, bounded by a surface called the event horizon, the point of no return. And physicists asked a deceptively simple question: how much information, how much entropy can a black hole contain? When you drop something into a black hole, its information seems to vanish behind the horizon. Where does it go? How much can the black hole hold? Working through the physics. In one of the most important theoretical achievements of the 20th century, they arrived at an answer, and the answer was deeply, profoundly strange. The information content of a black hole, its entropy, does not scale with its volume the way it does for everything else. It scales with the area of its surface, the area of its event horizon. Let that land, because it is the hinge on which this whole story turns. For every ordinary object, information scales with volume, with the three-dimensional space inside. But for a black hole, the most extreme gravitational object in the universe, the information scales with the two-dimensional area of its boundary. The amount of information a black hole can hold is determined not by how much volume is inside it, but by how much surface area wraps around it. It is as if all the information that fell into the black hole, all the three-dimensional contents, were somehow stored on the two-dimensional surface of the horizon, written across that boundary, rather than filling the volume within. The black hole behaves as though its information lives on its surface, not in its interior. And this was not a wild guess. It fell out of the rigorous combination of our best theories, the physics of gravity, of quantum mechanics, of thermodynamics, all pointing to the same astonishing conclusion. This was the clue, and it was a thunderbolt because it suggested that the natural place for information to live, at least for a black hole, is on a surface, on a boundary, on a two-dimensional sheet, rather than throughout a three-dimensional volume. And it raised an irresistible and vertiginous question. If the information content of a black hole is set by its surface area rather than its volume, is this a special quirk of black holes? Or is it telling us something deep and general about the nature of space and information's everywhere, something that applies not just to black holes, but to every region of space, including the room you are sitting in right now? Could it be that the information describing any region of reality is fundamentally limited by, and perhaps stored on, the surface that bounds it, rather than the volume it contains? That question, taken seriously, leads directly to the holographic principle and to the staggering possibility that the three-dimensional world is, at its foundation, a kind of projection from a two-dimensional surface. In the early 1990s, physicists took exactly that leap and stated it as a general principle. The idea, developed by several leading theorists, was this: the maximum amount of information that can be contained in any region of space is not set by the volume of that region, but by the area of the surface that bounds it. Any region, anywhere, not just a black hole. The room you are in, a galaxy, a single atom's worth of space. All of it. The information needed to describe everything inside any region can be fully accounted for by information on its two-dimensional boundary. They called it the holographic principle, precisely because of the analogy to a hologram. Just as a flat holographic film encodes a full three-dimensional image, the boundary of any region of space might encode everything happening in the three-dimensional volume within. The third dimension, the depth, the interior, might be, in a deep sense, reconstructible from information living on the lower dimensional surface. This is a breathtaking claim, and it is worth being precise about how radical it is. It does not merely say that you can describe the inside of a region using its boundary, the way you might describe the contents of a box, by listing what is on its walls. It says something far stronger, that the boundary contains the complete and full information of everything inside. That there is, in principle, no information in the volume that is not already captured on the surface. That the interior and the boundary are, in terms of their information content, equivalent. Everything that happens in the depth, every particle, every field, every event in the three-dimensional bulk has a complete description on the two-dimensional boundary. The volume holds no more information than its surface. The depth, in this informational sense, is redundant, already fully specified by the flat boundary that surrounds it. It is natural to resist this, and the resistance is instructive. Surely, you might think, the inside of a region contains more than its surface. Surely, a filled room holds more than could be written on its walls. Everything in our experience says so. But the holographic principle insists that this intuition, reliable as it is for everyday purposes, breaks down at the deepest level. It claims that there is simply no way to pack more independent information into a volume than its boundary can hold. That any attempt to do so, to cram in more and more detail, would eventually concentrate so much energy that the region would collapse into a black hole, at which point, as we saw, the information is governed by the surface area after all. The boundary is not just a convenient place to record a summary of the interior. It is the absolute ceiling on what the interior can contain, a hard limit written into the structure of space itself. The volume cannot outrun its surface. The depth cannot hold secrets the boundary does not already know. And this is why the word redundant is so carefully chosen and so jarring. In ordinary life, redundant means superfluous, extra, repeated unnecessarily. To say the third dimension is informationally redundant is to say something almost unbelievable, that the depth adds no new information beyond what the boundary already contains, that you could, in principle, throw away the entire three-dimensional description and lose nothing, because it is all there, complete on the flat surface. The depth would be like a faithful translation of a text that already exists in another language, adding no new content, only re-expressing what the boundary already fully says. This is not how depth feels. Depth feels primary, original, the place where things really are. But the holographic principle suggests that this feeling, however powerful, is the feeling of an emergent appearance, and that the original, the source, the place where the information truly lives, is the flat boundary we never see. Think about what this implies for the very idea of how much room there is in space. Our intuition says that a region of space can hold information proportional to its volume, that you could keep packing more and more detail into a region as you fill its three-dimensional interior. The holographic principle says no. It says there is a hard ceiling set by the surface area, and that ceiling is far lower than the volume would suggest. It says that the three-dimensional interior, vast as it seems, can hold no more information than can be written on its two-dimensional skin. And this is not a limitation of our instruments or our knowledge. It is, if the principle is correct, a fundamental feature of reality, a deep fact about the way the universe stores and organizes information, a fact that suggests the three-dimensional fullness of space is, at its foundation, an expression of something inscribed on a lower dimensional surface. There is a way to make this concrete that is both beautiful and dizzying. The black hole calculation does not just say that information scales with area. It tells you, in principle, how much information fits on a given amount of surface. And the answer is that the surface can be thought of as divided into tiny fundamental patches, each one almost unimaginably small, far smaller than an atom, smaller than the smallest scales we can probe, each patch holding a single basic unit of information, a single bit, the smallest possible yes or no of reality. The boundary, in this picture, is like a vast sheet covered in the finest imaginable pixels, each one carrying one bit, and the total information that can be described within is simply the number of these tiny pixels covering the boundary surface. The three-dimensional world inside, with all its richness, would be the unfolding of the information written across those countless minuscule patches. On the surface, the way a detailed image unfolds from the pixels of a screen, except that here, the pixels lie on a boundary, and the image is an entire three-dimensional world. And this leads to a thought that genuinely staggers the imagination. It suggests that there is a finite, definite amount of information that can describe any region of reality set by the area of its boundary, measured in these tiny fundamental pixels, and that this number, vast as it is for any large region, is far smaller than you would expect from the volume. The room you are in, by ordinary reckoning, contains an almost limitless amount of three-dimensional detail. But the holographic principle says the true information content is capped by the surface around the room, written in those impossibly fine pixels, and that everything within, every possible arrangement of everything in that space, is accounted for by that finite surface information. The depth, the volume, the three-dimensional fullness contains nothing extra beyond what the boundary already holds. It is a profound demotion of the volume and a profound promotion of the surface, a reversal of where we thought the substance of reality was kept. If you take this seriously, and physicists increasingly do, it inverts our entire picture of where reality lives. We naturally assume that the real action is in the volume, in the three-dimensional space, and that any surface or boundary is just a wall, a secondary thing, a mere edge of the real interior. The holographic principle suggests the reverse, that the surface may be where the fundamental information actually resides, and that the three-dimensional volume, the depth we live in, the space we move through, may be the secondary thing, the reconstruction, the projection, the emergent appearance generated by the information on the boundary, the world we inhabit, full and deep and three-dimensional, would be, in this view, like the floating image of the hologram, entirely real to our experience, but encoded at the deepest level on a flatter surface than we can ever perceive. And remarkably, this radical idea did not remain a vague philosophical suggestion. A few years later, a discovery in the mathematics of theoretical physics turned it into something concrete, precise, and astonishingly specific. In the late 1990s, a theoretical physicist working through the mathematics of string theory made a discovery that stunned the field and that remains to this day one of the most studied and celebrated results in all of theoretical physics. He found a precise, concrete, mathematically exact example of holography in action, a case where you could show in full rigorous detail that a universe with gravity and an extra dimension of depth was completely and exactly equivalent to a different description, living on its lower dimensional boundary, a description that had no gravity and one dimension. Two descriptions, utterly different on the surface, one with depth and gravity, one flat and without it, and yet mathematically identical, describing precisely the same physics, the same events, the same reality in two completely different languages. This is worth slowing down on, because it is the heart of why physicists take holography seriously, rather than treating it as mere speculation. Imagine a region of space with gravity, with objects moving through it, with all the rich three-dimensional physics you would expect, depth and all. And now imagine the boundary of that region, its lower dimensional surface. What this discovery showed is that there is a complete physical theory living on that boundary, a theory of particles and fields, with no gravity and one fewer dimension, and that this Amos boundary theory describes exactly the same situation as the gravitational theory in the interior. Every single thing that happens in the three-dimensional interior, every object, every motion, every gravitational effect, corresponds precisely to something happening in the flat, gravity-free boundary theory. The two are not similar. They are not approximations of each other. They are exactly the same physics, written two ways. Anything you can calculate in the deep, gravitational, three-dimensional picture, you can calculate equally in the flat, two-dimensional, gravity-free picture, and you get the same answer every time. It is hard to overstate how strange and powerful this equivalence is. So let us reach for an analogy, imperfect as any analogy must be. Imagine you had two books written in two completely different languages about two seemingly different subjects. One book describes, in vivid detail, the weather of an entire planet, its storms and winds, and shifting pressure, a rich, three-dimensional account of a turbulent atmosphere. The other book is a flat ledger of numbers, dry columns of data, with no mention of weather at all. Living on what amounts to a two-dimensional grid, they could not look more different. And yet, suppose someone showed you that the two books were secretly exactly the same, that every storm in the first corresponded precisely to a pattern in the columns of the second, that any question you could ask about the weather could be answered just as well by manipulating the dry numbers, and that the two were, in the deepest sense, identical descriptions of one single reality, merely written in different languages. You would be forced to conclude that the weather and the columns of numbers were not two different things, but one thing seen two ways, and that the rich three-dimensional weather was, in some sense, already fully contained in the flat ledger. This is the kind of equivalence the physicists discovered, except that the rich three-dimensional thing is a universe with gravity and depth, and the flat ledger is a theory living on its boundary. And the equivalence is not a loose resemblance or a poetic comparison. It is exact, demonstrated through detailed calculation. Physicists can take a hard question about black holes and gravity in the three-dimensional interior. One, they sometimes cannot easily answer in the gravitational language, translate it into the flat boundary theory, solve it there where it may be easier, and translate the answer back, and it works. They use this equivalence as a practical tool, a kind of dictionary that lets them move between the two descriptions, solving problems in whichever language is easier. The fact that this dictionary exists and functions flawlessly, that the two utterly different descriptions can be translated into each other without any loss, is the strongest possible evidence that they truly are the same physics, that the depth and the gravity of the interior really are encoded completely in the flat boundary. It is one thing to suggest holography as a philosophical possibility. It is another to use it daily as a working tool that gives correct answers. That is the level at which physicists now take this idea. The implications of this are staggering, and they are precise rather than hand-waving. It means that, at least in this carefully studied case, the interior, with its depth and its gravity, is not something extra added on top of the boundary. It is the boundary, Seen another way, the depth and the gravity are not fundamental ingredients. They are encoded entirely in the flat boundary theory, and they emerge from it. The third dimension in this example is genuinely redundant in the deepest sense. There is a complete description of everything without it, living on the surface. The gravitational, three-dimensional world is a way of repackaging information that is fully present, with nothing lost, on the lower dimensional boundary. This is not philosophy. It is a mathematical equivalence, demonstrated in detail, checked in countless calculations, one of the most robust and productive ideas in modern theoretical physics. What makes this so philosophically explosive is the word equivalence, and it is worth being clear about why it is so much stronger than mere correspondence. If the boundary theory were just a useful model of the interior, a simplified stand-in that captured some features and missed others, that would be interesting but not revolutionary. We use approximate models all the time, but this is not an approximation. The two descriptions contain exactly the same information, answer exactly the same questions, agree in every detail without exception. Neither is more fundamental than the other in any way that the mathematics can detect. They are simply two complete and equally valid accounts of one single reality. And once that is true, a startling conclusion follows. You can no longer say that the three-dimensional interior with its gravity is the real thing and the boundary is a mere shadow of it, because you could equally say the reverse, that the flat boundary is the real thing and the depth is what emerges from it. The mathematics does not privilege one over the other, but the boundary has one fewer dimension and no gravity, which makes it the simpler, more economical description. And that is a powerful hint that the boundary may be the more fundamental one, with the depth and gravity of the interior being the emergent derived appearance. This is why physicists speak of the bulk, the three-dimensional interior, as emerging from the boundary rather than the other way around. It is not that the mathematics forbids the opposite reading. It is that the boundary description is more spare, requiring fewer ingredients, no gravity, one less dimension. And in physics, the simpler and more economical description is usually taken to be closer to the foundation. The depth and the gravity, in this view, are not basic features that the universe was built with, but rich consequences that unfold from the simpler, flat description. The way an elaborate melody unfolds from a simple mathematical ratio, or an intricate pattern unfolds from a few simple rules. The three-dimensional gravitational world would be the elaborate, emergent unfolding. The flat boundary would be the spare, fundamental seed. And we would be living in the unfolding, in the rich, emergent depth, with the spare, flat truth lying beneath us, unseen, more fundamental, and astonishingly simpler than the world it gives rise to. Now, an important honesty is required here, and we will return to it, but it must be flagged. The specific, exactly solved example involves a kind of space with particular mathematical properties, not identical to the space of our actual universe. The clean, precise version of the holographic equivalence was found in an idealized setting, a sort of mathematical laboratory chosen because the equations could be solved there. Whether and exactly how it applies to the real universe we live in, with its particular geometry and its expansion, remains an open and actively debated question. so we must not overclaim. But the discovery did something profound regardless. It proved that holography is not just a vague analogy or a wild guess. It showed that it is mathematically possible, in full rigorous detail, for a three-dimensional gravitational world to be exactly equivalent to information on a two-dimensional surface. It took the holographic principle from a startling suggestion to a demonstrated mathematical reality, at least in idealized cases, and it transformed how physicists think about space, gravity, and dimension itself. So let us follow the idea to its most profound implication, the one that truly reorders the mind, and ask what it would mean if holography is, in fact, how our universe works at its deepest level. It would mean that depth itself, the third dimension, the very space you reach your hand into, is not a fundamental feature of reality, but an emergent one. Emergent is a precise and important word here. It means something that arises out of and is built from more basic underlying ingredients. The way the wetness of water emerges from the behavior of countless individual molecules, none of which is itself wet. Wetness is real, but it is not fundamental. It is a property that appears when many simpler things are arranged in a certain way. The holographic principle suggests that depth and the three-dimensional space we inhabit may be emergent in exactly this sense, arising from the organization of information on a lower dimensional surface, real but not fundamental, a higher level appearance generated by something flatter and more basic underneath. And it gets stranger because physicists have begun to uncover hints of what that more basic underlying thing might be, what it is that weaves the boundary information into the appearance of three-dimensional space. The leading idea points to one of the most mysterious phenomena in all of physics: quantum entanglement, the strange connection by which particles can become linked so that their properties are correlated no matter how far apart they are. Remarkably, in the mathematical study of holography, it appears that the way information on the boundary is entangled, the pattern of these quantum connections, is precisely what determines the geometry of the interior space, the very structure of the depth. Where the boundary information is strongly entangled, the corresponding regions of interior space are connected close together. Where the entanglement is weak, the space is far apart or even disconnected. The startling suggestion is that space itself, the fabric of the three-dimensional world, the distances and the depth, may be woven out of quantum entanglement on the boundary, that the threads of these quantum connections are, in some sense, the threads from which space is sewn. This idea that space is built from entanglement is one of the most actively explored frontiers in theoretical physics right now, and it has a startling consequence that researchers have demonstrated in their mathematical models. If you take the boundary description and imagine gradually reducing the entanglement between two parts of it, dialing down those quantum connections, then in the corresponding interior space, the two matching regions begin to pull apart, the space between them stretching and thinning. And if you reduce the entanglement all the way to nothing, the two regions of interior space pinch off from each other entirely, becoming disconnected, as if the space between them had been cut. The connectivity of space, the very fact that one place is near another, that you can travel from here to there through a continuous expanse of distance, appears to depend on the entanglement of the underlying boundary information. Remove the entanglement, and space itself comes apart. It is as direct a demonstration as one could hope for that the fabric of space is not fundamental, but woven, and that the threads are these quantum connections. If that is true, then the smoothness and continuity of the space around you, the seamless way you can move your hand through the air, without encountering any gaps or seams or breaks, the unbroken expanse of distance stretching out to the horizon and beyond, all of it would be the macroscopic expression of an almost inconceivably vast and intricate web of quantum entanglement, holding the world together, knitting every point of space to its neighbors, weaving the continuous fabric we move through out of countless individual quantum threads. Space would not be the empty stage on which everything happens. It would be a structure, a tapestry, an emergent weave, as much a made thing as the cloth of a garment, built up from the entanglement of information on a boundary we cannot see. And the reason space feels so seamless and solid and continuous would be that the weave is so unimaginably fine, the threads so numerous and so densely interlinked, that we perceive only the smooth cloth and never the individual threads from which it is sewn. Take that in. It suggests that the space around you, the depth you move through, the distances between things, may be the large-scale expression of a vast web of quantum entanglement. That what we experience as the smooth, continuous, three-dimensional fabric of space is woven from countless quantum connections. At a deeper level, the way a smooth piece of cloth is woven from countless individual threads. This way of thinking turns the familiar idea of empty space completely on its head. We tend to think of space as the absence of things, as nothingness, as the empty container in which objects sit and events happen, the one thing that is definitely not made of anything. But if space is woven from entanglement, then space is not nothing at all. It is a richly structured something, a vast and intricate web, as much a real physical entity as the matter within it, perhaps more so. The emptiness between the stars, the empty air of your room, the gap between your hand and the page, would all be, in this view, not absence but presence, a dense weave of quantum connections, so fine and so seamless that it presents itself to us as empty space. The void would be full of the very threads from which distance and depth are sewn. There would be no true emptiness anywhere, only the woven fabric, sometimes carrying matter and sometimes not, but always there, always structured, always the real and active foundation of the world, rather than its mere backdrop. And if that is so, then the most ordinary thing imaginable, the empty space in front of your face, would be one of the most remarkable and least appreciated objects in existence. A marvel of quantum structure, a fabric of staggering intricacy that we pass through without a thought, never suspecting that the very emptiness is woven. We reach through it constantly, move through it, live our entire lives immersed in it, and we call it nothing, when it may be one of the richest somethings there is. To grasp the holographic picture is to lose, forever, the ability to see empty space as merely empty, and to gain instead a sense of being always surrounded by an invisible, intricate weave, the deep structure of reality, present in every gap and every distance, holding the whole world together. And gravity, Two in this picture would be emergent, not a fundamental force pulling things together, but a consequence of how this entangled information is arranged. The curving of space that we call gravity arising from for the deeper organization of the boundary, the two great pillars of our experience of the physical world. The depth of space and the pull of gravity would both be emergent phenomena, real but not fundamental, surface appearances generated by the entanglement of information on a lower dimensional boundary we can never directly see. If this is right, then the world is far stranger at its foundation than anything our senses suggest. The solid, deep, three-dimensional reality we inhabit, with its gravity and its distances and its fullness, would be the emergent surface appearance of a reality whose true description is lower dimensional, flatter, woven from quantum entanglement, organized in a way that bears no resemblance to the world we perceive. We would be living inside the reconstructed image, the projection, the emergent depth, real in every way that matters to our experience, but underlain by something utterly different, a flat web of quantum information from which our entire three-dimensional world arises. The depth would be real, but it would be the surface of something deeper, or, rather, something flatter, the appearance generated by a reality we are only beginning, through mathematics, to glimpse. Of all the things that might be emergent, gravity is perhaps the most surprising. And it is worth dwelling on, because gravity has always seemed like the most fundamental force of all. It shapes the orbits of planets, holds galaxies together, governs the expansion of the universe itself, the grandest and most universal of forces. And yet, in the holographic picture, gravity is not a basic ingredient written into the laws of nature, but an emergent phenomenon, a large-scale consequence of how information is organized and entangled on the boundary. The bending of space that we experience as gravity, the force that holds you to your chair, and the earth to the sun, would arise from the deeper informational structure, the way the pressure of a gas arises from the motion of its molecules, real and powerful and everywhere, but not fundamental, a derived effect rather than a basic law. This idea that gravity is emergent rather than fundamental is one of the most actively pursued in theoretical physics, and the holographic principle is one of its main inspirations, suggesting that the most universal force we know may itself be a surface expression of something deeper and flatter. If both space and gravity are emergent, then nearly everything we think of as the basic furniture of physical reality, the stage and the most fundamental force acting upon it, would be revealed as derived, secondary, emergent from a flat informational foundation that contains neither space as we know it nor gravity as we know it, but only quantum information and its entanglement, from which both space and gravity bloom. The fundamental description of reality, in this view, would be almost unrecognizable to us, containing none of the features we consider most basic, no depth, no gravity, just a pattern of information on a surface from which our entire rich, deep, gravitating world emerges. It is a picture of reality so far from ordinary intuition that we can barely hold it in mind. And yet it is where the mathematics points, a foundation stranger than the world it founds, flatter and simpler and utterly alien, giving rise to everything we know. Now, This is the point where the idea can tip over into something frightening or disorienting. And so it is the point where we most need to be careful and clear, because the holographic principle is very easily and very commonly misunderstood, and the misunderstanding can turn a beautiful piece of physics into a source of needless dread. So, let us be precise about what this does and does not mean. It does not mean that you are not real. It does not mean that the world is an illusion or a fake, or that nothing truly exists. This is the crucial point. Remember the word emergent. The wetness of water is emergent, arising from molecules, not fundamental, and yet water is genuinely, really wet. You can drown in it. You can drink it. Its wetness is entirely real, even though it is not fundamental. The temperature of the air is emergent, arising from the motion of countless molecules, and yet the warmth you feel is real warmth. Emergent does not mean fake. It means real, but built from something deeper. And so it is with depth and space, if holography is correct. The depth of the room is real depth. The space you move through is real space. You are a real, three-dimensional being having real experiences in a real world. The theory does not take any of that away. What it says is that this real, three-dimensional world may be built upon and encoded in a deeper layer that is lower dimensional. The way real wetness is built upon molecules, the reality of your world is not in question. Only its ultimate foundation is revealed to be stranger than it appears. Consider how many of the things you care about most are, in exactly this sense, emergent and lose nothing of their reality for it. A piece of music is emergent. It arises from individual notes, from vibrations in the air, none of which is itself music. And yet the music is real, able to move you to tears, entirely genuine, even though it is not a fundamental ingredient of the universe, but something that emerges when sounds are arranged just so. A conversation is emergent, arising from words, which arise from sounds, which arise from air molecules in motion. And yet the conversation is real, meaningful, capable of changing your life. The beauty of a face, the meaning of a story, the bond between two people, all of these are emergent, built from simpler things that do not individually contain them, and not one of them is any less real for being so. Emergence is not the enemy of reality. It is one of its most common and most beautiful modes. The universe is layered with richer and realer things emerging at every level from the arrangement of simpler things beneath, and we live among these emergent realities all the time, never doubting that they are real, never feeling cheated that they are built from something more basic. So, if depth and space are emergent, arising from a flat web of quantum information, they take their place among all these other emergent realities, no less real for their emergence, no more an illusion than music or warmth. The three-dimensional world would simply be one more, and perhaps the grandest of the universe's emergent layers, the rich appearance that arises when the underlying boundary information is arranged in a certain way, as real as anything can be at the level we live, and built, like everything else, from something deeper. There is nothing diminishing in this, nothing that should disturb us. It places our three-dimensional world exactly where it belongs, among the real, layered structures of a universe that builds richness upon richness, and that may build even depth itself out of something flatter and more fundamental beneath. This distinction matters enormously because without it, the holographic principle sounds like a claim that we are trapped in some kind of fake, that nothing is real, that we are mere shadows or projections in the dismissive sense. That is not what it says, and that misreading is worth firmly setting aside. The hologram analogy can mislead here, because an everyday hologram is just an image with no substance. But the holographic principle is not saying the world is a mere picture. It is saying that the full, substantial, real, three-dimensional world may have its complete description encoded on a lower dimensional surface, the way the full information of a thing can be captured in more than one form, without the thing being any less real. You are not a flickering image. You are a real being whose deepest description may simply be organized in a way that is lower dimensional than your experience. The world loses none of its solidity, none of its reality, none of its weight. It gains instead a hidden depth, or rather a hidden flatness, an underlying structure of breathtaking strangeness beneath its familiar surface. The world you can touch remains entirely real and entirely yours. Only its foundation is revealed to be stranger and more wonderful than you knew. And once you hold that distinction clearly, the vertigo can transform into something else, something closer to wonder. Because what the theory really offers is not a demotion of reality, but a deepening of it. The discovery that the world we know so well may rest on a foundation utterly unlike itself, that beneath the obvious three-dimensional surface of things lies a layer of reality so strange that we can barely describe it, a flat web of quantum information from which our entire rich world emerges. The world is not less for this. It is more. It is realer and stranger at once, the familiar depth we trust, revealed to be the surface of a mystery. The solid world we inhabit, shown to be the emergent face of something we are only beginning to comprehend. That is not a reason for fear. It is a reason for awe. And it is worth saying plainly that the fear, when it comes, is almost always based on the misunderstanding we have just cleared away. The mistaken idea that emergent means fake, that holographic means imprisoned, that to be a projection is to be unreal. Strip away that misunderstanding, and the fear has nothing left to stand on. What remains is simply a deeper picture of a reality that was always there, a richer understanding of the same trustworthy world. Nothing has been taken from you. The room is as solid as it ever was. Your life is as real as it ever was. The people you love are as real as they ever were. All that has changed is that you now glimpse, beneath all of it, a foundation of extraordinary elegance and strangeness. And that glimpse is a gift, not a loss, an addition to your understanding, not a subtraction from your reality. The proper response to a gift is not dread, but gratitude and wonder, and that is exactly the response the holographic principle deserves, once it is understood correctly. So let the fear go, if it arose, and let the awe take its place. You have not been told that you live in a lie. You have been shown that you live in a mystery, which is a very different and far more wonderful thing. A lie diminishes, a mystery enlarges. To live in a lie would be to have your reality stolen. To live in a mystery is to have your reality deepened, to discover that the ordinary world is the surface of something profound. The holographic principle, rightly understood, offers the second, not the first. It does not steal your world. It deepens it immeasurably, revealing the familiar to be the visible face of a reality stranger, and more beautiful than you knew, and inviting you not to fear, but to marvel. It is important, too, to be honest about exactly where this idea stands, because honesty is what separates real science from empty mystery-mongering, and the true status of the holographic principle is itself fascinating. This is not a confirmed fact about our universe. It is a profound and well-motivated theoretical idea, supported by powerful mathematics in certain idealized settings, but not yet established as the actual description of the reality we live in. We must hold it with the right mix of seriousness and humility. What is on solid ground is the black hole result, the discovery that a black hole's information scales with its surface area rather than its volume. That is derived from our best theories and is widely accepted. Also, on remarkably solid ground is the precise mathematical equivalence discovered in the late 1990s, the demonstration that, in a particular idealized kind of space, a gravitational three-dimensional world is exactly equivalent to a flat boundary theory without gravity. That equivalence has been checked and used in thousands of calculations, and is regarded as one of the most reliable and productive tools in theoretical physics. So the core idea that holography is mathematically possible, and even exactly realized in idealized cases, is firmly established. What remains open and genuinely uncertain is whether and exactly how this applies to our actual universe. The clean, exactly solved example involves a space with a particular curvature that differs from the geometry of the real cosmos, which is expanding and shaped differently. Translating the precise holographic equivalence to our own universe is one of the great unsolved problems that physicists are actively working on, and no one yet has a complete agreed answer. The difficulty is worth understanding because it is not a vague hand wave, but a specific mathematical obstacle. The idealized space in which the holographic equivalence was first proven has a particular kind of curvature, a sort of inward curving geometry that gives it a well-defined boundary, a natural surface on which the flat description can live. It is, in a sense, a space neatly wrapped in a boundary, which is exactly what holography needs. But our universe does not appear to have that geometry. Our universe is expanding, and not just expanding, but expanding at an accelerating rate driven by the mysterious dark energy, which gives it a different kind of curvature, an outward-tending geometry that does not come with the same kind of tidy boundary. Where, in an expanding universe like ours, would the holographic surface be? What would play the role of the boundary on which our world is encoded? These are genuinely hard questions, and the clean mathematical machinery that works so beautifully in the idealized case does not simply carry over. Physicists are working to extend holography to spaces like ours, exploring various candidate surfaces and modified versions of the principle. But the matter is unsettled, so the honest picture is layered, and it is worth holding all the layers at once, rather than collapsing them into a simple yes or no. At the deepest level of confidence, we have the black hole result and the exact equivalence in idealized space, both firmly established, both telling us that holography is real and possible and exact true in certain settings. At the next level, We have a strong and widely shared intuition among physicists that something holographic is going on in our universe too, because the black hole result that started it all applies to real black holes in our real cosmos, and because the idea has proven so deep and so fruitful. And at the outermost level, we have the genuine, unresolved question of exactly how holography works for a universe shaped like ours. A question being actively investigated. To say the universe may be a hologram is to point to this whole layered situation, to a serious idea grounded in solid results and pushing into open territory, not to a settled fact and not to mere fantasy, but to something in between, which is exactly where the most exciting science always lives. It is healthy when sitting with an idea this large to keep a clear head about the difference between what is demonstrated and what is conjectured, because the holographic principle is sometimes presented as though it were established fact, and at other times dismissed as though it were pure fantasy, and neither extreme is right. The truth is more disciplined and more interesting than either. We have hard, demonstrated results, black hole information scaling with area, and the exact equivalence in idealized space. We have a well-motivated and widely held expectation that something similar holds more broadly, and we have honest, open uncertainty about the details for our own universe. Holding those three things together, refusing to overstate and refusing to dismiss, is what it actually looks like to think clearly about a frontier idea. The dread that the holographic principle sometimes inspires often comes from imagining it as a proven, total claim about reality. Seen accurately as a serious idea with solid roots and open branches, it is far less a source of fear and far more a source of fascination, an invitation to watch a great question being worked out in real time. And there is a reason to expect that we will learn more, that this will not remain forever a matter of speculation. Physics has a long record of taking questions that once seemed purely philosophical, unanswerable, beyond the reach of evidence, and gradually turning them into questions with real answers, pinned down by mathematics and observation. The nature of light, the age of the universe, the existence of atoms, all were once thought to lie beyond what we could ever know, and all yielded, in time, to patient inquiry. The question of whether our universe is holographic may follow the same path, moving from speculation toward something firmer as the mathematics develops and as we learn to connect it to what we can observe. We are, in a sense, watching the early chapters of that story, present at the beginning of an inquiry that may, in time, give a definite answer to one of the deepest questions there is. And whatever that answer turns out to be, the fact that the question has become askable at all is a quiet triumph worth savoring. So when we say the universe may be holographic, we are describing a serious, mathematically grounded possibility that many leading physicists find compelling, and that the evidence points toward not a proven fact. It might turn out that our universe is holographic in essentially the way the idealized cases suggest. It might turn out to be holographic in some modified or more subtle way. Or there might be surprises that reshape the picture entirely. The honest answer is that we do not yet know, and that this is one of the live frontiers of physics being explored right now. And there is something wonderful in that honest uncertainty rather than something disappointing. It means We are living in the middle of one of the great unfolding investigations into the nature of reality, watching as physicists, armed with mathematics and black hole physics, and the strange logic of quantum information, probe the question of whether the depth of our world is fundamental or emergent, whether reality is what it appears or something far stranger underneath. The question is open. The answer is not yet written, and the mere fact that the question can be asked rigorously, that we have found mathematical worlds where holography is exactly true, that our own most extreme objects hint in the same direction, is itself astonishing. We have reached, with our theories, all the way down to the question of how many dimensions reality fundamentally has. And we have found that the answer is not obvious, that the depth we take for granted may be a surface effect, and that the truth lies somewhere we are still carefully and brilliantly trying to reach. It is worth understanding why physicists were driven to such a strange idea in the first place, because they did not arrive at holography out of a desire to be shocking. They were pushed to it reluctantly by a deep problem, a paradox at the intersection of our greatest theories. The problem concerned black holes and information, and it kept some of the finest minds in physics awake for decades. Here was the puzzle. Our theory of the quantum world holds as a sacred principle that information is never truly destroyed. The details of a system may be scrambled beyond recognition, but in principle, the information is always preserved, never erased. And yet, black holes seem to violate this. When something falls into a black hole, its information appears to vanish behind the horizon, and when the black hole slowly evaporates away over immense time, as the physics says it must, the information seemed to be lost entirely, erased from the universe, in flat contradiction with the quantum principle that information cannot be destroyed. To feel the force of the paradox, you have to appreciate how seriously physicists take the principle that information is never destroyed. It is not a minor technical rule. It is woven into the deepest structure of quantum mechanics, the theory that underlies all of modern physics, and that has passed every experimental test ever devised. The principle says that if you knew the complete state of a system perfectly, you could in principle run the laws of physics backward and reconstruct its entire past. That nothing is ever truly lost, only rearranged. Burn a book, and it seems the information in it is gone. But in principle, if you could track every particle of smoke and ash and every photon of light emitted, the information would still be there, scrambled but recoverable. This is a bedrock commitment. And black holes seem to violate it at the most fundamental level, not scrambling information, but apparently destroying it outright, which would mean the laws of physics break down, that the past becomes unrecoverable, that the whole logical structure of the theory fails. That is why it was a crisis and not a curiosity. The crisis deepened with the realization, worked out in the 1970s, that black holes are not truly black and eternal, but slowly radiate energy and shrink, evaporating over almost inconceivable spans of time until they vanish entirely. This was a profound discovery in its own right, that black holes have a temperature, that they glow faintly, that they are not permanent. But it sharpened the paradox to a knife's edge. For if a black hole swallows information and then, over the eons, evaporates away to nothing, where does the information go? The radiation it gives off as it evaporates appeared, in the original analysis, to be featureless, carrying no trace of what had fallen in. So when the black hole finally disappeared, the information seemed to disappear with it, gone for good. A book dropped into a black hole, then would have its information truly erased from the universe once the black hole evaporated, in direct violation of the principle that this can never happen. Two of our deepest theories, quantum mechanics and gravity, stood in open contradiction, and the conflict could not be wished away. This was not a small puzzle. It was a genuine crisis, a place where two of our deepest theories, quantum mechanics and gravity, gave contradictory answers, and resolving it became one of the great quests of theoretical physics. And the holographic principle emerged in large part as a response to this crisis. If the information that falls into a black hole is somehow stored on its surface, on the two-dimensional horizon, rather than lost in the depths within, then perhaps it is not destroyed. After all, perhaps it can be preserved and eventually released, and the contradiction can be resolved. The idea that information lives on the boundary was not invented to be strange. It was reached for as a possible solution to a deep and stubborn problem, a way to save the principle that information cannot be destroyed. And in pursuing that solution, physicists were led, step by step, to the broader and more radical idea that information living on boundaries might be a general feature of reality, not just a property of black holes. So the holographic principle was born not from idle speculation, but from the hard labor of trying to reconcile our deepest theories, from following the mathematics where it led, even when it led somewhere deeply counterintuitive. It is the product of decades of work by many brilliant physicists, building on one another's insights. The black hole entropy result, the bold statement of the principle, the precise mathematical equivalence, the connection to entanglement, each step hard-won, each one pushing the idea from suggestion toward serious theory. This is how the strangest ideas in physics usually arrive, not as wild guesses, but as the reluctant conclusions of people, following rigorous reasoning into territory they never expected to enter, forced by the mathematics to consider possibilities that overturn their intuitions. The physicists who developed holography were not trying to tell us the world is strange. They were trying to solve a problem, and the solution turned out to be stranger than any of them would have chosen. This is, in fact, a hallmark of genuine discovery, as opposed to mere invention, and it is one of the things that should make us take the idea seriously rather than dismiss it as fanciful. When people make things up, they tend to make up things they find appealing or comfortable or dramatic in a way they enjoy. But the deep results of physics have a different character. They are frequently unwelcome, counterintuitive, resisted even by the very people who discover them. The physicists who found that information lives on the boundary did not want that to be true. Many of them spent years trying to find some other resolution, some way to preserve the comfortable picture in which depth is fundamental and information fills volume. They were dragged to holography by the mathematics against their preferences, the way earlier physicists were dragged, reluctantly, to the strange truths of relativity and quantum mechanics. That reluctance is a sign of authenticity, an idea that its own discoverers found unsettling. that emerged not from desire, but from the relentless logic of equations, has the fingerprints of reality on it, the mark of something found rather than wished into being. There is a humility in this that is worth honoring, the humility of letting the universe overrule your intuitions. It would have been easier, in every way, to declare the black hole information paradox unsolvable, or to insist that depth must be fundamental because it so obviously seems to be, and to refuse the strange conclusion. Instead, a generation of physicists did the harder and more honest thing. They followed the reasoning wherever it led, accepted conclusions that overturned their deepest assumptions, and built, step by careful step, a serious theory out of an idea that affronts common sense. That willingness to be led by evidence and logic into deeply uncomfortable territory is the engine of all real progress in understanding the world. And the holographic principle is one of its most striking products, a conclusion no one wanted, reached because the universe seemed to insist on it. And there is something deeply moving in that, in the image of the human mind, confronted with a paradox at the edge of knowledge, following reason and mathematics with such fidelity that it is willing to conclude, if that is where the logic leads, that the very dimensionality of reality is not what it seems. It is a triumph of intellectual honesty, of letting the universe tell us what it is rather than insisting it conform to our intuitions. The holographic principle may or may not turn out to be the final truth about our universe, but the fact that we were able to reach it at all, to follow our theories down to the question of whether depth is fundamental, is a testament to how far the careful, honest, collective work of physics can carry us, all the way to the threshold of a reality stranger than we ever imagined. Let us step back then from the mathematics and the black holes and the paradoxes and simply sit for a moment with the sheer wonder of what we have been describing, because it is easy to get lost in the strangeness and miss the beauty. We live in a world that presents itself to us as obviously, undeniably three-dimensional, a world of depth and distance and solid space, and for the whole of human history, no one had any reason to question that this was the bottom layer of reality, the way things simply are. And then, through nothing but careful thought, through following the logic of our best theories about gravity and quantum mechanics and information, we stumbled onto the possibility that this most basic fact about the world might not be fundamental at all, that the depth might be a surface effect, that reality might be written at its foundation on a flatter sheet than we can perceive. To have reached such a possibility, to have found mathematical worlds where is it exactly true, is one of the most extraordinary achievements of the human intellect, a reaching down past the surface of things to question the very framework in which we exist. And whatever the final answer turns out to be, the journey itself reveals something profound about the universe and about us. It reveals that reality is not obligated to be the way it appears, that the most basic features of our experience, even something as fundamental as the number of dimensions space has, can turn out to be emergent, surface expressions of something deeper and stranger underneath. It reveals that the world has hidden layers, that beneath the familiar there may be the utterly unfamiliar, that the solid ground of our intuitions may rest on foundations we never suspected. This is, in a way, the deepest lesson of all of physics, repeated again and again throughout its history. That the world is stranger than it looks, that the surface of things conceals depths, or, in this case, flatnesses, that we could never have guessed, and that careful inquiry can carry us, astonishingly, down toward those hidden layers. Think of how many times this has happened, how reliably the universe has turned out to be stranger than the appearances suggested. The solid ground beneath our feet felt perfectly still, and yet we'd learned that we are riding a spinning planet hurtling around the sun at enormous speed, the sun itself racing around the galaxy, the whole thing in ceaseless motion beneath the illusion of stillness. Matter felt solid and continuous, and yet we learned it is almost entirely empty space, a sparse scattering of tiny particles. Time felt absolute and universal, the same for everyone, and yet we learned it stretches and bends, running at different rates for those moving differently. At every turn, the most basic and obvious features of reality, the ones that seemed beyond all doubt, turned out to be appearances concealing a stranger truth beneath. The holographic principle, if it holds, is simply the latest and perhaps the most dramatic entry in this long history. The discovery that even the dimensionality of space, even the depth we move through, may be one more appearance with a deeper and stranger reality underneath. And there is a pattern in this history that should give us a certain confidence, even comfort. Each time we have discovered that reality is stranger than it looks, the world has not collapsed. Our lives have not become meaningless. The ground has not actually given way beneath us. We learned the Earth was spinning and racing through space, and we went on, walking and building and loving, exactly as before. The new knowledge sitting alongside the unchanged texture of daily life. We learned matter was mostly empty space, and tables went on holding up our meals. Each revelation of hidden strangeness left the surface of life intact, adding wonder without subtracting reality, so we can expect the same of holography. Should it turn out that depth is emergent and reality is encoded on a distant surface, the world will go on exactly as it always has, solid and deep and trustworthy. At the level we live, the strange new truth resting quietly beneath, one more layer of hidden wonder in a universe that has always had more layers than we knew. There is a particular kind of awe that comes from this, different from the awe of vast size or great power, the awe we might feel before a giant star or a black hole. It is the awe of depth, of discovering that the reality we thought we understood completely is, at its foundation, a profound mystery, that the very stage on which everything happens, space itself, may be an emergent appearance, woven from something we are only beginning to grasp. It is the awe of realizing that we live every day inside a reality whose true nature is stranger than any story, that the ordinary room around you, the ordinary depth you move through, may be the surface of something extraordinary. And this awe does not require the theory to be finally proven. It is enough that the question is real, that the possibility is serious, that the universe has shown us, through the mathematics of black holes and entanglement, that the depth we trust may not be the whole story. We are used to locating mystery far away, in distant galaxies, in the depths of black holes, in the first moments of the cosmos, in places remote from our ordinary lives. But the holographic principle relocates the mystery to somewhere far more intimate and far more startling. Right here, in the space immediately around you, in the very depth you are looking into at this moment. The greatest mystery is not light years away. It may be the few feet of air between you and the nearest wall, the ordinary depth of the ordinary room, which could be one of the most profound and least understood things in all of existence. There is no need to travel to the edge of the universe to stand at the frontier of the unknown. The frontier is here, in the space you inhabit, in the depth you take entirely for granted, which may be the surface of the deepest secret there is. To realize this is to find the extraordinary hiding inside the ordinary, the cosmic mystery folded into the most mundane feature of your immediate surroundings. And this, perhaps, is the most wonderful thing the holographic principle offers, beyond all its specific claims about black holes and boundaries and dimensions. It returns a sense of mystery and depth to the ordinary world, restores the strangeness to the familiar, reminds us that we live every single day, surrounded by and immersed in something we do not fully understand, and that may be far more marvelous than we ever imagined. The space around you is not a settled, fully understood backdrop. It is a live question, a deep mystery, possibly the surface of an extraordinary hidden reality. And do not have to go anywhere to be in the presence of that mystery. You are in it now, surrounded by it, part of it, an emergent being in an emergent space, living at the heart of one of the deepest wonders there is, in the most ordinary moment of the most ordinary day. To live with this awareness is not to be frightened or unmoored. It is to walk through the world with a kind of doubled vision, seeing the familiar surface and sensing, beneath it, the deeper mystery, appreciating the solid three-dimensional world for the real and wonderful thing it is, while knowing that it may rest on a foundation of breathtaking strangeness. It is to hold both the surface and the depth at once, the everyday and the profound, the world as it appears and the world as it may fundamentally be. And there is a richness in that doubled vision, a sense of living in a reality far more interesting and mysterious than we usually allow ourselves to notice, a reality whose every ordinary moment is underlain, perhaps, by one of the deepest secrets there is. What does it mean, then, for you, sitting here, to live inside a reality that may be holographic in this deep sense? It means something that is, when you really consider it, more intimate and more astonishing than any abstract theory has a right to be. It means that the depth you reach into when you extend your hand, the space between you and the things you love, the three-dimensional fullness of every moment of your life, may be the emergent surface of a reality encoded on a boundary you will never see. It means that you, a real being having real experiences, may be, at your deepest foundation, woven from a web of quantum information, organized in a way that has no depth at all, your three-dimensional existence, a true and beautiful emergence from something flatter and stranger. You are not diminished by this. If anything, you are deepened, revealed to be a more remarkable thing than you knew, a real, full, three-dimensional being arising from a foundation of profound and elegant strangeness. And notice that none of this changes a single thing about how you live or how you should feel about your life. And that is part of its beauty. Whether or not depth is fundamental, the embrace of someone you love is exactly as real, exactly as warm, exactly as meaningful. Whether or not space is emergent, the beauty of a sunset, the taste of food, the sound of music, the weight of a held hand, all of it is precisely as real and precisely as valuable as it ever was. The holographic principle, if true, operates at a level so far beneath ordinary experience that it leaves the entire human world untouched, intact, fully real. It does not reach up to diminish your life. It only reveals, far below, a foundation more wonderful than expected. The depth of your world is real. The richness of your experience is real. And underneath, perhaps, lies a flatter, stranger, more elegant reality that makes the whole thing possible. The way the silent dance of molecules makes possible the warmth you feel without making that warmth any less real. It is worth pausing on how rare and precious it is to live at a moment when such a question can even be asked seriously. For almost the entire span of human existence, the nature of space and dimension was simply a given, an unquestioned backdrop, beyond the reach of inquiry. People could wonder about it, could spin myths and speculations, but no one could investigate it, could bring evidence and mathematics to bear, could distinguish a serious possibility from an idle dream. And now, in our time, after centuries of patient work, building up the theories of gravity and quantum mechanics and information, we have arrived at a place where the question of whether depth is fundamental has become a real scientific question, with real tools to attack it, real results bearing on it, real progress being made. You are alive at the moment when humanity first gained the ability to seriously ask whether the dimensionality of a reality is what it seems, and to begin haltingly to answer. That is an extraordinary moment to be present for, and you are present for it, able to understand, at least in outline, one of the deepest investigations our species has ever undertaken. And there is something fitting, even beautiful, in the fact that this deepest of questions connects directly to the things closest to you, the depth you reach into to embrace someone, the space across which a voice travels to reach your ear, the distance between you and the window, between the earth and the moon, between one galaxy and the next. All of this depth, the intimate and the cosmic alike, would be, in the holographic view, the same emergent thing, the same unfolding of information from a boundary, woven from the same quantum threads. The space of your bedroom and the space between the stars would be facets of one emergent fabric, the near and the far, the small and the vast, all of it the surface appearance of a single flat foundation. There is a kind of unity in that, a sense that the depth of your most ordinary moments and the depth of the entire cosmos are made of the same deep stuff, that you are woven into the same fabric as the farthest galaxies, an emergent pattern in the same great weave that gives rise to all of space, everywhere. And perhaps that is the most quietly beautiful consequence of all. If depth is woven from a single underlying fabric, then the separateness we feel, the sense of being isolated points scattered across an indifferent void, is itself only the surface appearance. Underneath, at the level of the boundary, everything that is near in space is bound by the same threads, knit into the same continuous weave, so that the apparent gaps between things are spanned at the deepest level by the connections from which the gaps themselves are made. You are not a lonely speck adrift in empty distance. You are part of a seamless fabric, joined to everything around you, by the very threads that make distance possible, woven into the same cloth as the room, the sky, the stars. The depth that seems to separate you from the world may be, at its foundation, the very thing that binds you to it. There is a deep reassurance available in understanding this correctly, and it is the opposite of the dread the idea can first inspire. The reassurance is that the strangeness lies underneath, supporting and enabling the world, not replacing or negating it. You are not living in a deception. You are living in a real world that has at its foundation a structure more beautiful and more surprising than your senses reveal. And that is, when you think about it, a wonderful situation to be in, to inhabit a reality that is both completely real at the level you experience it and profoundly mysterious at the level beneath, to be a genuine three-dimensional being whose existence rests on one of the most elegant and astonishing possibilities in all of physics. The hologram, if that is what we are part of, is not a prison or a lie. It is a marvel, and we are real within it, and the depth we live in is ours to enjoy, fully and without fear, whatever it may rest upon. So you can let the eye settle into something gentle, even as it remains profound. The next time you reach into the space in front of you, the next time you notice the depth of a room or the distance to the horizon, you can let yourself feel, for just a moment, the possibility that this depth is the emergent surface of something flatter and deeper, a thought that need not frighten you, but can fill you with a quiet wonder at the sheer strangeness and richness of the reality you are part of. And then you can let the thought go and return to the solid, real, three-dimensional world, which is waiting for you exactly as it always was, unchanged, undiminished, yours to live in, now, carrying just a little of the mystery you have glimpsed beneath it. It is fitting that thoughts like these tend to come most powerfully in the quiet of the night, when the busyness of the day falls away, and the mind has room to wander out toward the deepest questions. In daylight, surrounded by the solid business of life, the idea that depth might be emergent seems almost absurd, too strange to take seriously. But at night, in the stillness, lying in the dark with the day behind you, the strangeness becomes easier to feel. The ordinary certainties loosen a little, and you can sense, just at the edge of thought, the genuine mystery beneath the familiar surface of the world. The night is when the great questions breathe, when the mind can hold the possibility that reality is far stranger than it appears, and when that possibility, rather than disturbing, can become a source of quiet wonder, a companion to the darkness and the silence. And so, as the night deepens around you, let yourself rest in the strangeness gently, without any need to resolve it, somewhere far beneath the level of your senses, beneath the level of atoms and particles, beneath even the level of space itself. There may lie a flat boundary, a web of quantum information, from which the entire three-dimensional world, including you, emerges. You will never see it. You will never perceive it directly. But it may be there, the deepest foundation of everything, holding up the depth you live in the way a loom holds the threads of a cloth. And you are part of it, an emergent pattern of breathtaking richness, a real and full and three-dimensional being woven from something flatter and stranger, living your real life on the surface of a profound mystery. There is nothing in that to fear. There is only the wonder of being part of a reality so much deeper and stranger than it seems. And notice that you have lived your entire life atop this possible foundation without ever needing to know about it. Perfectly well, perfectly happily. The depth of the world serving you faithfully every moment, whether or not it is fundamental. Every step you have ever taken through space, every reach of your hand, every glance across a room, every embrace, every journey, has worked exactly as it should. The depth always there, always reliable, always real to your experience, regardless of what underlies it. The possible holographic foundation has changed nothing about how the world has served you, and it will change nothing going forward. This is perhaps the gentlest way to hold the whole idea, that it describes a layer so far beneath your life that your life has never once depended on, knowing about it, and never will. The world has always worked and will keep working exactly the same, whether its depth is fundamental or emergent, whether it rests on a boundary or on something we cannot yet name. There is a quiet kind of trust that this makes possible, the trust of someone who has learned that the strangeness of the foundations not reach up to disturb the solidity of the floor. You can know, intellectually, that the depth of the world may be one of the strangest things in all of physics, and at the very same time lean back into that depth with complete confidence, resting in it, moving through it, relying on it, exactly as you always have. The knowledge and the trust do not conflict. The physicist who studies holography by day still walks home through real space at night, still leans on the real depth of the real world, still lives, like everyone, in the trustworthy three-dimensional fullness of things. The deep strangeness is for contemplation, for wonder, for the quiet hours. The solid world is for living in, always available, always reliable, never withdrawn. You can have both, and you do. Let the solidity of your world hold you as it always has. The bed beneath you is real and holds your weight. The room around you is real and full of its real depth. The distance to the wall is a real distance, the space a real space, and you can trust all of it, lean on all of it, exactly as you always have, because none of it is taken away by the possibility that, far underneath, it rests on a flatter foundation. The reality you can touch and feel and live in is yours, fully and without question. And the deeper reality, the one the physicists chase through their equations, is not a threat to it, but its hidden support. The elegant strangeness from which your solid, trustworthy, three-dimensional world arises. You can rest in the world precisely because the world is real, whatever it may be made of underneath. There is a profound peace available in that, if you let yourself feel it, the peace of trusting the world while remaining open to its mystery. You do not have to choose between the solid reality you live in and the deep strangeness beneath it. You can have both, holding the everyday world close and trusted, while letting the deeper mystery be a distant, gentle wonder, a thing you know is there without needing to grasp it. This is, in the end, a comfortable way to live with one of the strangest ideas in all of physics, to keep the world you love exactly as real and solid as it has always been, and to let the deep strangeness rest quietly underneath, supporting it. A secret foundation you can marvel at from time to time and then set gently aside, returning always to the warm, real, three-dimensional life that is and remains entirely yours. If anything, an idea like this can make the ordinary world more precious rather than less, because it reveals the hidden depth in the most familiar things. The next time you walk through a doorway, you might feel, just faintly, the wonder of moving through emergent depth, of passing through a space that may be woven from quantum threads on a distant boundary. The next time you watch something recede into the distance, growing smaller as it goes, you might sense the strangeness of that depth, the possibility that it is the surface expression of a flatter reality beneath. None of this will change what you do. You will still walk through the doorway, still watch the distance, still live your ordinary life. But the ordinary life will carry, underneath it, a thread of wonder it did not have before, a quiet awareness that the simplest features of the world are among the deepest mysteries there are. That is a gift the holographic principle can give, even unproven, even uncertain. The gift of seeing the familiar world as the marvel it may truly be. And so the strangeness, far from making the world cold or frightening, can make it warmer and more wonderful, a place of hidden depth and innocent mystery, where most ordinary moment is shot through with the possibility of something profound. You do not have to choose between living comfortably in the world and marveling at its depths. The two go together, the comfort and the wonder, the solid floor and the deep mystery beneath it, and you can hold them both as you move through your days and nights, at home in a world that is exactly as real as it has always been, and far stranger and richer than you ever knew. So let your thoughts slow now, and let the great strangeness soften into the quiet of the night. You have traveled tonight to one of the furthest edges of human understanding, to the very question of how many dimensions reality has at its foundation. And you have seen that the answer is not what anyone expected, that the depth we take for granted may be the emergent surface of a flatter, deeper, stranger reality, a cosmic hologram in the truest and most serious sense. It is one of the most profound ideas the human mind has ever reached, and you have held it and looked at it and seen both its vertigo and its wonder, and now you can let it rest. Picture it one last time, softly, without fear, the whole rich, deep, three-dimensional world, all of space and everything in it, encoded perhaps on a distant boundary, a flat surface woven of quantum information, from which the depth emerges like an image blooming from a holographic film. And you, real and whole, living in that emergent depth, a genuine being having genuine experiences, resting on a foundation of breathtaking elegance you will never see. The world is real. You are real. And underneath, perhaps, lies a mystery more beautiful than any answer we expected, holding everything up, asking nothing of you, simply being the deep, strange truth of the reality you are part of. There is nothing you need to do with this knowledge tonight. The physicists will go on with their equations, chasing the question of whether and how our universe is holographic, working at the live frontier of the deepest mystery there is, whether or not anyone is watching. The boundary, if it is there, will go on holding up the depth, silent and unseen as it always has. And you can simply let it all be, the surface and the depth, the world and its foundation, and turn toward rest, a real being in a real world, carrying now a little of the wonder of having glimpsed how strange that real world may be underneath. Let the depth of the room hold its quiet mystery. Let the space around you be both completely real and profoundly strange. And let that be enough, without resolution, without worry. You are here, whole and three-dimensional and real, resting in a world you can trust, beneath which lies, perhaps, one of the most elegant secrets in all of existence. And that is a good thing to know as you drift towards sleep, not a thing to fear, but a thing to wonder at. The gentle and astonishing possibility that the solid world you live in is the surface of something deeper, that reality is richer than it seems, and that you are a real and remarkable part of it, now and through the whole of the quiet night, exactly as you always have been, exactly as you always will be, here, real and at peace in the depth of the world.